G'day guys. Alright, so today we're starting to look at geometric sequences. Okay, now the first thing we looked at was arithmetic sequences, which is when you have a beginning term, a starting term, and then you add a common difference onto that starting term to get the second term, and then you add on the common difference, the same common difference, to get the third term, and then add the same d value to get the fourth term, and so on. And then we did arithmetic series, which is simply when you add together all of the terms in an arithmetic sequence. Now today we are doing geometric sequences, and this will lead into geometric series. So this there's some nice symmetry between what we're doing now and what we've done already. Now a geometric sequence is when you have a starting value, and to get the next value in your sequence, you multiply by what we call a common ratio. So it's a common ratio instead of a common difference. And then that gets you your second term. To get the third term, you multiply by the same common ratio, the same number. To get the fourth term, you multiply the third term by the same common ratio, and so on. So let's begin with the definition. A geometric sequence is a sequence in which each term is found by multiplying the previous term by a fixed amount. And here we have an example: 5, 10, 20, 40. So the fixed amount that the previous term in each case is being multiplied by is obviously 2. Because to get from 5 to 10, you multiply by 2. To get from 10 to 20, multiply by 2. From 20 to 40, multiply by 2. Okay? Now, as was the case for arithmetic sequences, we have two ways of representing these bad boys. Okay? We have a recurrence relation and an explicit formula. A recurrence relation, once again, is what enables you to find, let's say, the 50th term if you know the 49th term. So it lets you find the next term in terms of the previous term, if you have the previous term. An explicit formula allows you to find just the 100th term or the 1000th term, any term you want, so long as you have the starting value and the common ratio, which is the number that we multiply each term by to get the next number. Let's look at the recurrence relation first. So here it is here. It has two parts once again. T1, so you need the first term to define a recurrence relation. So T1 equals A in the general case, but that would, in a specific case, be T1 equals, well, let's look at the example above. That would be T1 equals 5 for this example here. And then we need Tn in terms of the previous term, Tn minus 1. So what this here is saying is that the next term, Tn, equals the previous term multiplied by some common ratio r. And if we look at our example up here, we can see that that is the case. Tn, let's say this term here, is equal to the previous term, Tn minus 1, multiplied by a common ratio, which is 2 in this case. 5 times 2 equals 10. Alright, so what about the explicit formula? Well, the explicit formula is that the nth term, Tn, equals A multiplied by r to the power of n minus 1. Now that n minus 1 confuses people a lot. So we can flick over here for a moment and talk about that, break it down a little bit and talk about that in a little bit more detail. So here we have a very basic example of a geometric sequence. The numbers in the top row are the terms in the sequence, and you can see in purple there I've labelled them. So we have T1 is 3, T2 is 6, T3 is 12, T4 is 24, and so on, all the way up until some Tn. And in the bottom row we have n, the term number. First term, oh whoops, that's not what I wanted. First term, second term, third term, fourth term, etc. All right, so let's see if we can build our way up to a formula for Tn just by looking at this example, okay? So what do we have? We have T1 equals 3 in this particular example. The first term is 3. Now, T2 equals 3 times the common ratio. And what is the common ratio? Well, it's obviously 2, because 3 multiplied by 2 gets us to 6. 6 multiplied by 2 to 24. By 2, to 12, and then by 2 again to 24. Okay, so R is equal to 2. So the second term is A multiplied by the common ratio 2, and that's it. Now the third term is whatever the second term is multiplied by the common ratio again. But the second term is 3 times 2. Okay, and if the third term is 3 times 2 times 2, then we need to add in another times 2. But that looks goofy. 3 times 2 times 2. I might as well write 3 times 2 squared. All right, so now we're getting somewhere. Now T4 is going to be whatever T3 was multiplied by another 2. Now T3 was 3 times 2 squared, and I have to multiply that by the common ratio to get T4. But once again, that looks a little goofy. 3 times 2 squared times 2. So why not rewrite it as 3 times 2 cubed? All right. Now, you're going to see a pattern here. When we get all the way down to Tn, what are we going to have? We are going to have 3 times 2 to the power of what? Well, here's the thing. Let's look at the powers of 2 and compare them to the n value, the corresponding n value. So when n is 4, the power on 2 here is 1 less. When n is 3, the power on the 2 here is 1 less than 3. When n is 2, the power on the 2 here, which is 1, is 1 less than that. Okay? So this power is always 1 less than n. So Tn, for this example, is going to be 3 times 2 to the n minus 1. And this is always going to be the case. Now 3 was just our beginning value, our starting value. And 2 was just our common ratio. So in general, what can we say? Well, in general, the nth term is always going to be your starting value, your first term, multiplied by the common ratio to the power of n minus 1. Boom. So not exactly a proof, but I'd say solid evidence and enough information for you to understand why that formula works. All right, it's time to start doing some examples. So, practice problem 1. Find the 13th term in the following geometric sequence. Minus 2, minus 6, minus 18, and so on. All right, so the first thing we want to write down is what our A value is and our R value. Our A value is minus 2. That's the first term. Now, in an arithmetic sequence, to get the common difference, we would do T2 minus T1, or we would do T3 minus T2. Okay, we do something similar for geometric sequences, except instead of minus, we do divide. So we want to do T2 divided by T1. So minus 6 divided by minus 2, which equals 3. And if you do T3 divided by T2, minus 18 divided by minus 6, so long as it's a geometric sequence, then you'll get the exact same thing, okay? You'll get 3. Okay. So now all we have to do is remember our formula. Tn equals AR to the n minus 1. So T13, where after the 13th term, equals A times R to the n minus 1, 13 minus 1. I could have just directly written in 12, but these are our notes, so I'm trying to be really explicit with my setting out. So that becomes minus 2 times 3 to the power of 12. Bust out your calculator, you get negative 1,062,882. And that is that. All right, question 2. 30.375 is the sixth term in a geometric sequence. The first term is 4. Find R, the common ratio. All right, so let's write down everything that we have. We have the first term is 4. We have the sixth term, which is 30.375. And I'm just going to scribble over to the side here because we also have a formula. Tn equals AR to the n minus 1. Now, what are we actually after here? We are after R. That's what we're being asked for. We have the nth term, okay? Or we have a term. We have T6. And so long as we substitute in 6 for this n value here, then we're all good. And we have the first value, A. So that will just leave one unknown, R. And we'll be able to solve for it. So here we go. T6 equals what they told us, which equals A times R to the 6 minus 1. In other words, 5. And that's just a simple equation now. So we divide both sides by 4, and we get R to the power of 5 equals this business. I won't bother stating the decimals. Now, if you know R to the power of 5 equals that, then R on its own is the fifth root of the right-hand side of the equation. In other words, R equals that same number to the power of 1 on 5. So put that into your calculator and you get, lo and behold, a lovely non-recurring decimal, 1.5 exactly. All right, question 3. For the geometric sequence 36, 18, 9, etc., the nth term, some term, we're just going to, for the time being, call the nth term, is equal to 9 on 16. Find the term number that corresponds to that term, okay? Find n. All right, well, what do we have? We have A, which is 36. We have R, which is 18 divided by 36, or 9 divided by 18, which gives us a half. And we have Tn equals 9 on 16, which in turn equals AR to the n minus 1. So A times R to the n minus 1. We don't know what n is yet, so we just leave it in there. So now we have an equation with one unknown that we can solve. Now, the problem is the unknown, the variable that we need to solve for, is an exponent. It's an index, a power, okay? And there's a whole branch of mathematics that enables you to solve when the variable is a power, and that's called logarithms. And you probably haven't done that unless you've done a little bit in methods. But luckily with this particular example and the particular examples that they give you in the textbook, there's a trick. And if you can't use this trick, then you can use your CAS calculator, just the solve function. But let me show you the trick, because this question has been designed to just work out perfectly, okay? All right, so here we go. Now, the first thing I do is divide both sides by 36 so that I get the bracket half to the n minus 1 on its own. So I get that on its own equals 9 over 16 divided by 36 gives you 9 over 576. Now I'll just keep the left-hand side the same for the time being. Now that 9 over 576 simplifies to 1 over 64. All right. Now, in the brackets on the left-hand side, I have 1/2. Now, 1 over 64, that can also be written as 1/2 to a power, okay? And that is if you look up here, 1/2 to the power of 6, because 64 is 2 to the power of 6, and 1 to the power of anything equals 1. So 1/2 to the power of 6 equals 1 over 64. Now, whenever you have something, some base raised to a power equals the same base raised to a power, then those two powers must be equal because the bases are the same. So now you can drop out the bases and I can make the claim that n minus 1 is equal to 6. And if n minus 1 is equal to 6, add 1 to both sides, we get n equals 7. And we've answered the question. So that wasn't too bad after all. Question 4. The third term in a geometric sequence is 10 and the sixth term is 80. Find the common ratio and the first term. All right, well, what have they told us? T3 equals 10, but we know that Tn equals AR to the n minus 1, 1 less than n. So if we have T3, then T3 must equal AR to the power of 2, because 2 is 1 less than 3. And that is equal to 10, because they say so. So we have that equation. They also tell us that T6 equals 80, but we also know that T6 must equal A times R to the 6 minus 1, which is 5. So we have this second equation, 80 equals AR to the power of 5. Now this should look very familiar to you because we now have a pair of simultaneous equations, and we did a very similar thing with arithmetic sequences. So now if I do equation number 2 divided by equation number 1, all right, then I get AR to the 5 over AR squared, and the A's cancel out, equals 80 over 10. Now R5 over R2, that's our second index law. That becomes R to the power of 5 minus 2, which is R cubed. And 80 divided by 10 is 8. So R cubed equals 8, so R equals 2. And let me just explain that actually, because people get confused by this. If R cubed equals 8, what do you have to do to R to get rid of that 3? Well, if you remember your index laws, powers outside of brackets multiply by powers inside of brackets. And 3 times a third is 1, which will get us exactly what we want. But then we have to do it to the right-hand side. So we have to also apply power of a third to the 8. Now, power of a third is the same as the cube root. So we now get R to the power of 1, which is what we want, equals the cube root of 8, which is 2. So R equals 2. Then we simply substitute R equals 2 into either of our equations and solve for A. And we get A equals 5 on 2. Nice and straightforward. And just to talk about this question a little bit further, guys, you could actually now go ahead and find the nth term. And quite often that's what the question would be. They'll tell you the third term and the sixth term. Find the formula for the nth term, because it's just Tn equals AR to the n minus 1. So our formula would be Tn equals 5 over 2, that's A, times R, which is 2, to the power of n minus 1. And then we could use that formula to find any term we wanted, 100th term, 59th term, whatever, okay? All right, question 5. Now, question 5 gives you a glimpse into why sequences and series is the natural branch of mathematics to deal with financial questions. When you do further math, if you do further maths, the whole finance topic is actually sequences and series, which is really, really interesting. Because if you do finance in general, you don't see any sequences and series. You see a bunch of formulas that the teachers just give you, which don't make any sense, but which mysteriously work. So hopefully some of this financial stuff might actually start to make a bit more sense. So let's look at a question. Tom invests $2,500 at 7% per annum compounding annually. Okay, per annum means per year. So Tom, at the beginning of the first year, say, has $2,500 and he invests that in a deal where it will grow by 7% each year. So that 2,500 will grow by 7%. And then at the start of the next year, he'll have a bit more than 2,500. And that amount, which is a bit more than it was previously, will in turn grow by another 7%. So it's exponential growth. All right. Find the value of his investment after 5 years. After 5 years. Something very important about that wording there, which we'll get to. All right. So let's turn this into a geometric sequences problem. A is 2,500, which is the amount he had at the beginning of the first year. And R is 1.07, because if you want to increase $2,500 by 7%, you have to multiply it by 1.07, don't you? Not 1.7, that would mean an increase of 70%. All right, so what is the value of the investment after 5 years? Now, no matter how much I try to explain this, students still sometimes don't understand because it's really tricky. After 5 years is going to mean that we have to find the 6th term in the sequence. And let's think about that for a moment. The first term is 2,500. That's how much he had between, now count on your fingers, the 0th year and the first year. So when the clock started and the end of that year. So between 0 and 1 years. So that's term 1. Term 2 is between 1 year and 2 years, the amount that he had. Term 3 is between 2 and 3 years. Term 4 is between 3 and 4 years. Term 5 is between 4 and 5 years. And term 6 is between 5 and 6 years. So term 6 is the amount that he has from the start of the 5th year to the end of the 5th year, when the 6th year starts. So after 5 years exactly, okay, we are looking for the 6th term. Now, you're going to have to mull over that yourselves a little bit because I know it's confusing as hell, okay? But T6 equals AR to the 6 minus 1, which is power of 5. So we get 2,500 times 1.07, which equals $3,506.38, which is the amount of his investment after 5 years. That's how much it's grown to. Pretty tricky, I know. Now, question B, how long does it take for his investment to reach a value of $10,000? Well, a little bit later down the track, I'll show you how to do this on your CAS calculator, but you can do it by trial and error, actually, by just testing a bunch of different n values in your calculator until you get close to 10,000. So if I pick n equals 21, obviously I built up to that with 18, 19, 20. So if n equals 21, I get AR to the 21 minus 1, so 2,500 times 1.07 to the power of 21 minus 1, which is just less than $10,000. But as soon as I go from n equals 21 to n equals 22, I get 2,500 times 1.07 to the 22 minus 1, which is just over $10,000. So n equals 22 is the magic number where his investment has reached, for the first time, a value of $10,000. But remember, n equals 22 corresponds to the 22nd term. So we're talking about 21 years for the same reason that I explained in the previous question. So it will take 21 years for the investment to be worth more than $10,000. All right, we're getting there, guys. I know this is a long one. Now, Geometric mean. We looked at the arithmetic mean in a previous lesson, which said if you have 3 consecutive terms in an arithmetic sequence, then the term in the middle is equal to the average, the mean, of the 2 terms on either side. Something very similar is true when it comes to geometric sequences, but it's called the geometric mean. Let's do a little proof. So A, C, and B are consecutive terms, so they're terms in a row in that order, A, C, B, in a geometric sequence. Might be at the beginning, in the middle of the sequence, or at the end, it doesn't matter. So what then can we say about that relationship? Well, C divided by A will give you your common ratio, and B divided by C will give you your common ratio. So C over A and B over C are both equal to R, so they must equal each other. C over A equals B over C. Now, if I simply multiply both sides of that equation by C, and I multiply both sides by A, in other words, this C comes up here, and this A comes up here, I get C squared equals AB. Then all I have to do is take the square root of both sides, and I get C equals the square root of AB, which is kind of another type of average, another type of mean, okay? So what's our conclusion? C is the geometric mean of A and B. So if you know that you have let's say T5 and T7 of a geometric sequence, then T6 will equal the square root of the product of those two. Nice little result there. And just to tie things off with a practice problem along those lines, the 6th and 8th terms of a geometric sequence are 5 and 720. So 5 is the 6th term, 720 is the 8th term. So find the geometric mean of these two and hence determine the 7th term. So 7 is right in between 6 and 8. So we know that the 7th term is going to be the square root of the product of the 5th and the 8th terms. So the square root of 5 times 720 equals 60. In other words, T7. We've found T7. T7 equals 60. All right, guys. I think that was the longest one of these things we've done. Thank you for paying attention. Good luck, and I will see you next time.